A solar cell thinner than a human hair, flexible enough to wrap around a curved surface, light enough that a square meter of it weighs less than a sheet of cardboard, and efficient enough to convert over 33% of the sunlight hitting it into electricity, a number that shatters every record ever set by a commercially manufacturable photovoltaic device. This is not a laboratory curiosity destined to stay behind glass in a research institution.
This is a technology that manufacturers are actively scaling right now, that has already broken world records verified by independent testing institutes, and that could fundamentally change what solar power looks like on buildings, vehicles, aircraft, satellites, and eventually, every surface that sees sunlight. The manufacturing process behind it is so intricate, so layered with atomic scale precision, that even engineers who have spent decades in the solar industry describe it as operating at the absolute edge of what industrial chemistry can achieve. By the end of this video, you'll know exactly how it's made. To understand why tandem flexible solar cells matter, you need to understand a fundamental limitation that has constrained solar energy since the very first silicon panel was manufactured in the 1950s. Every photovoltaic material has what physicists call a band gap, a specific energy threshold that determines which wavelengths of sunlight it can absorb and convert into electricity. The problem is that sunlight is not a single wavelength. It's a broad spectrum, from ultraviolet through visible light all the way into infrared. A single material with a single band gap can only efficiently convert a portion of that spectrum. The rest of the energy, the photons that are either too energetic or not energetic enough for the material's band gap, is wasted as heat. This is why the theoretical efficiency limit for a single-junction silicon solar cell, the Shockley-Queisser limit, sits at around 33%, and why even the best commercial silicon panels in the world struggle to exceed 24 or 25% in practice. The tandem approach solves this problem with breathtaking elegance. Instead of one material trying to capture the entire solar spectrum, you stack two materials with different band gaps on top of each other. The top layer captures high-energy photons, the blue and green end of the spectrum. The lower energy photons that pass through the top layer are captured by the bottom layer, which is tuned to a lower band gap. Together, they harvest a far wider swath of the solar spectrum than either could alone. In theory, a two-junction tandem cell can reach efficiencies approaching 45%. In practice, the best tandem cells, combining perovskite with silicon, have already demonstrated certified efficiencies above 33%. And the leading research groups believe 35 or even 36% is achievable in the near term. Now add flexibility, the ability to manufacture this two-layer system on a substrate that bends and flexes rather than rigid glass or silicon wafer, and you have something genuinely transformative. A solar material that is simultaneously more efficient and more versatile than anything that came before it. The materials story begins in some unexpected places. The bottom subcell in most commercial tandem flexible designs uses crystalline silicon, the same fundamental material as conventional solar panels, but processed into thin films or engineered into structures that can accommodate some mechanical flexibility without fracturing. Silicon is refined from silicon dioxide, essentially refined sand, through a highly energy-intensive process called the Siemens process, in which silicon tetrachloride, or trichlorosilane, is reduced to pure silicon in reactors operating at temperatures over 1,000 degrees Celsius. The resulting polysilicon is then either grown into single crystal ingots using the Shockley-Queisser process, or cast into multi-crystalline blocks, then sliced into wafers as thin as 150 micrometers, thinner than 2 human hairs stacked together. For tandem flexible applications, research programs have explored making these silicon wafers even thinner, or using heterojunction silicon architectures that achieve excellent electronic performance at thicknesses where some mechanical compliance becomes possible. The top subcell, the one that captures high-energy photons and passes the rest through to the silicon below, is where the real revolution is happening. Perovskite. The name refers not to a single compound, but to a crystal structure. the same atomic arrangement found in the mineral calcium titanate, first described by the Russian mineralogist Lev Perovskite in the 19th century. In the context of solar cells, perovskites are typically methylammonium lead iodide, or related compounds, hybrid organic-inorganic materials that can be synthesized in solution at relatively low temperatures and deposited as thin films on a wide variety of substrates. The band gap of a perovskite solar absorber can be tuned by changing its chemical composition. Substituting different ions into the crystal lattice shifts the band gap across a wide range, allowing engineers to design the top cell's absorption range to complement the silicon bottom cell precisely. This tunability is one of the most remarkable properties of the perovskite family, and a key reason why it has become the dominant candidate for the top subcell in commercial tandem solar devices. But this is where things get interesting. Perovskite solar cells have a reputation in the research community that combines extraordinary promise with extraordinary fragility.
The best perovskite cells in the laboratory have demonstrated efficiencies above 26% as single-junction devices, remarkable for a material that was barely considered for photovoltaics before 2009. But perovskite crystals are sensitive. They degrade when exposed to moisture. They can degrade under prolonged illumination. The lead in the most efficient formulations raises environmental and regulatory concerns. And the jump from making a small cell the size of a postage stamp in a laboratory to coating square meters of the material uniformly on a moving, flexible substrate in a production environment involves manufacturing challenges that have consumed years of engineering effort and hundreds of millions of dollars of research investment. The companies and institutions that have cracked the stability and scaling problems simultaneously, achieving both high efficiency and long operational lifetime in a form that can be manufactured at scale, are operating at the absolute frontier of industrial chemistry.
The raw material inputs for the perovskite layer are themselves remarkable. Lead iodide and methylammonium iodide, the most common precursor chemicals for the classic perovskite absorber composition, are synthesized from lead compounds and organic precursors, dissolved in polar solvents such as dimethylformamide or dimethyl sulfoxide, and prepared as a coating solution with precisely controlled concentration and composition. The lead content that makes these cells so efficient is also the subject of intense regulatory scrutiny. European environmental regulations under the RoHS directive have historically limited lead in electronics, and exemptions for perovskite solar cells have been a subject of active policy debate. In parallel, researchers have pursued lead-free perovskite compositions, substituting tin, bismuth, or antimony for lead. But these alternatives have so far underperformed the lead-based materials in efficiency. The path to mass market deployment of lead perovskite solar cells runs directly through regulatory frameworks in Europe, Japan, and North America, adding a policy dimension to the technical and manufacturing challenges. The flexible substrate that carries both cells, the foundation that everything else is built on, is another critical materials choice. For truly flexible tandem cells, the substrate must be mechanically compliant, thermally stable enough to survive the processing temperatures of the layers deposited on it,
transparent if light must pass through the substrate side first, and chemically inert to avoid reactions with the active layers. Polyethylene terephthalate, PET, the same material in plastic bottles, is one common substrate for lower temperature processes. Polyethylene naphthalate, PEN, offers better thermal stability. Ultra-thin flexible glass, at thicknesses below 100 micrometers, combines the chemical stability and barrier properties of glass with enough flexibility to be rolled and bent. Some of the most advanced tandem flexible designs use ultra-thin flexible glass as the primary substrate, achieving a combination of optical clarity, hermeticity, and mechanical flexibility that polymer substrates struggle to match. Each of these substrate materials arrives at the production facility on large rolls, the roll-to-roll manufacturing paradigm that the flexible solar industry is built around. Roll-to-roll processing is the manufacturing approach that makes flexible solar cells economically viable. Instead of processing individual rigid wafers or panels in batch processes, loading them into a reactor, processing them, unloading them, repeating,
Roll-to-roll manufacturing runs a continuous web of flexible substrate through a series of deposition and processing stations, applying layer after layer as the material travels through the production line.
Think of it like a printing press, but instead of printing ink onto paper, you're depositing precisely engineered semiconductor layers onto a flexible web moving at controlled speed. The economic logic is compelling. A roll-to-roll production line operates continuously, depositing material at speeds that can reach several meters per minute across web widths of a meter or more. The throughput of a mature roll-to-roll line is dramatically higher than batch processing for the same capital equipment cost. The challenge is that every layer must be deposited with perfect uniformity across the entire web width, at every point along the web length, without any variation that would create non-uniform performance across the finished product. The manufacturing process for a perovskite silicon tandem flexible cell starts with the silicon heterojunction bottom cell, which is built on the ultra-thin silicon wafer, or flexible silicon substrate, using a series of plasma-enhanced chemical vapor deposition steps. Thin amorphous silicon layers, doped to create the PN junction that drives the photovoltaic effect, are deposited on both sides of the silicon absorber. The temperature of this deposition process must be kept below approximately 200 degrees Celsius to preserve the electronic passivation quality of the hydrogenated amorphous silicon layers.
On top of the silicon subcell, transparent conductive oxide layers, typically indium tin oxide or aluminum-doped zinc oxide, are sputtered to create electrical contacts that are both conductive and optically transparent, allowing light to pass through to the active layers below. However, the next step is where the manufacturing complexity reaches a completely different level. Depositing the perovskite top cell on top of the completed silicon bottom cell requires threading a needle between multiple competing constraints simultaneously. The perovskite deposition must happen at temperatures the silicon bottom cell can survive. The solvents used in solution-based perovskite deposition must not attack the layers already present. The crystallization of the perovskite film must be rapid and uniform, because a perovskite film with inconsistent crystal grain size across its area will produce inconsistent efficiency, and the coating must be free of pinholes that would allow electrical shorting. And all of this must happen in a controlled atmosphere, because perovskite crystallization is exquisitely sensitive to humidity. Even a small fluctuation in ambient moisture during deposition can cause crystal defects that permanently degrade cell performance.
The deposition methods being pursued by the leading tandem flexible manufacturers fall into two main categories. The first is solution processing, dissolving the perovskite precursors in solvent, coating the solution onto the substrate using slot die coating, blade coating, or inkjet printing, and then carefully controlling the drying and annealing conditions to achieve the desired crystal structure. The slot die coating approach, borrowed from the display and packaging industries, pumps the perovskite solution through a precision-machined die head that deposits a uniform liquid film across the full web width. The film then passes through a precisely temperature-controlled drying zone where the solvent evaporates at a controlled rate. Too fast and the crystallization is disordered. Too slow and productivity collapses. The second approach is vapor deposition, evaporating the perovskite precursor compounds in vacuum and allowing them to condense onto the substrate as a thin film. Vapor deposition produces extremely uniform, pinhole-free films and avoids the solvent handling challenges of the wet process. But the capital equipment for large-scale vapor deposition is expensive, and the deposition rates are lower than solution processes. At this point, one tiny mistake could ruin the entire product. Between the silicon bottom cell and the perovskite top cell sits a layer that most people never hear about, but that is absolutely critical to the performance of the tandem device: the recombination junction, also called the tunnel junction or interconnect layer. In a tandem cell, the photocurrent generated by the top cell must combine with the photocurrent generated by the bottom cell, and this happens through this ultra-thin interlayer. If the recombination junction has too much electrical resistance, it creates a parasitic voltage loss that drags down the overall efficiency. If it has too little selectivity, It allows recombination losses that waste carriers. The materials used, typically combinations of nanocrystalline silicon, titanium dioxide, or specialized organic transport layers, must be deposited with atomic-level precision at thicknesses of just a few nanometers. A variation of even a single nanometer in this layer's thickness across the device area can create measurable efficiency non-uniformity in the finished cell. Now for the most impressive part. The encapsulation system that protects a finished Perovskite silicon tandem flexible cell from the environment is an engineering masterpiece in its own right.
Perovskite is sensitive to oxygen and moisture. Degradation begins within minutes if the active layer is exposed to humid air. The encapsulation barriers required to achieve a commercially viable outdoor lifetime of 25 years or more must limit moisture permeation to levels so low they are almost beyond the capability of conventional measurement, a water vapor transmission rate below 10 to the -6th grams per square meter per day. For context, the permeation rate of common plastic films is typically millions of times higher than this. Achieving the required barrier performance requires multi-layer encapsulation systems using atomic layer deposition, a technique that builds nanometer-thick films of alumina or other inorganic barrier materials literally one atomic layer at a time, in a self-limiting surface reaction that automatically stops after each monolayer is complete. These atomic layer deposition steps alternate with thin polymer planarization layers to smooth any surface defects that could create pinholes in the barrier stack. The completed barrier structure might contain dozens of alternating inorganic and organic layers, each only a few nanometers thick, combining into a total encapsulation structure that is still flexible enough to survive thousands of bending cycles.
The quality control process for tandem flexible solar cells operates at length scales that challenge conventional metrology. Electroluminescence imaging, passing current through the cell and imaging the light emitted, reveals non-uniformities in crystal quality and defect concentrations that are invisible under normal illumination. Photoluminescence mapping, illuminating the cell with a laser and mapping the emission spectrum, reveals variations in the band gap and carrier lifetime across the cell area. Lock-in thermography, applying a modulated electrical signal and mapping the thermal response with an infrared camera, identifies resistive losses and shunts with spatial resolution of fractions of a millimeter. Every one of these techniques must be adapted for a flexible, large-area web product rather than a rigid laboratory sample, requiring innovations in how the measurement is performed, how the substrate is held flat during imaging, and how the data is processed to provide actionable feedback to the production process. Here are the facts that put the ambition of this technology in perspective. The world record certified efficiency for a Perovskite silicon tandem cell has been pushed above 33%, verified by the Fraunhofer Institute for Solar Energy Systems, a number that was considered theoretically difficult to approach for commercial devices just 5 years ago. The top perovskite layer in a high-efficiency tandem cell is between 500 nanometers and 1 micrometer thick, roughly 1/100th the width of a human hair, yet it absorbs more than half the energy the device extracts from sunlight. A roll-to-roll tandem flexible production line operating at a web speed of just 2 meters per minute and a web width of 1 meter can theoretically produce enough solar cell area in a single day to cover the roof of over 1,000 homes. The atomic layer deposition barrier systems protecting these cells deposit films at a rate of 1 angstrom per cycle, 1/10,000,000th of a meter per deposition cycle, yet must be applied across a web that might be hundreds of meters long. The indium used in the transparent conductive oxide layers of these cells is one of the rarest elements in the Earth's crust, more scarce than silver, and almost entirely produced as a byproduct of zinc smelting, creating supply chain vulnerabilities that researchers are racing to address by developing indium-free alternatives.
The global landscape for tandem flexible solar cell manufacturing is intensely competitive and geographically concentrated. Chinese companies, including LONGi Green Energy, which currently holds multiple silicon-based solar efficiency records, and a constellation of well-funded startups have invested heavily in tandem perovskite silicon development.
European programs, centered in Germany, the Netherlands, and Switzerland, have produced some of the fundamental scientific advances that underpin the technology. American companies, including First Solar, the dominant thin-film solar manufacturer, and a range of venture-backed startups, are pursuing their own approaches. South Korean and Japanese electronics companies, with decades of experience in thin-film deposition from the display industry, have natural manufacturing competencies that translate directly into perovskite film production. The supply chain for critical inputs, high-purity lead iodide, specialty solvents, ultra-thin flexible glass, atomic layer deposition equipment, is globally distributed, but concentrated in a small number of specialized suppliers, creating both dependencies and opportunities for companies that secure these inputs early. The applications unlocking with this technology are not incremental improvements on rooftop solar panels. They are genuinely new categories of solar deployment.
Building integrated photovoltaics, solar cells incorporated directly into roofing membranes, facades, and windows during building construction, become far more practical when the solar material is light, flexible, and available in rolls that can be laminated or adhered to existing surfaces. Vehicle integrated solar, covering the curved surfaces of car roofs, hoods, and trunks, becomes meaningfully productive with cells exceeding 30% efficiency, potentially adding tens of kilometers of range per day from ambient sunlight. Lightweight solar for drones, high-altitude pseudo-satellites, and stratospheric aircraft, applications where every gram matters, becomes viable when the power output per kilogram reaches levels that heavy, glass-encapsulated panels cannot approach. And space applications, where launch cost makes specific power, watts per kilogram, the dominant metric, are transformed by solar films that weigh a fraction of conventional spacecraft solar panels while delivering record efficiency. From silicon refined out of ordinary sand through energy-intensive chemical processes, to lead iodide crystals grown in solution with atomic-level compositional control, to perovskite films deposited in humidity-controlled environments on flexible substrates, moving through production lines at the speed of a slow walk, to encapsulation barriers built one atom at a time, the tandem flexible solar cell is the product of a manufacturing chain that operates simultaneously at the scales of chemistry, nanotechnology, and industrial production. It is a technology that exists right at the boundary between what science says is possible and what engineering has managed to achieve. Every new efficiency record is a message to the world that the boundary is moving, and it is moving fast. The solar revolution that most people imagined was already finished, panels on rooftops, farms, and deserts, is actually still at its beginning. The cells being made today are so different from what was available a decade ago that the comparison barely holds. And the cells being developed right now in the laboratories and pilot lines that will become tomorrow's gigafactories are different again. What part of this technology surprised you most? The efficiency numbers, the manufacturing process, or the applications it makes possible? Tell us in the comments. And if this opened your eyes to how deep the solar revolution actually goes, a like and a subscription keeps this channel at the cutting edge.